We're going to work on partial pressures and gas stoichiometry. Okay, Dalton's law of partial pressure says that the total pressure in a container is the sum of the pressures of all the components. So what we see here is that if we have 1 atmosphere of one gas plus 1 atmosphere of a second gas, then the total pressure inside the container is 2 atmospheres. So basically what it boils down to is if you look at PV equals nRT, the only thing that's varying are the moles for each component. But the R and T and V, since they're in the same container, same volume, same temperature, are constants. So if you look at this, and we can walk it through, so we did this already. So we're combining each species. If we combine the ones that are constant, so that leaves us with the ones that are changing. So that gives us the number of moles total, RT. So the pressure total is equal to the total number of moles using the gas. Okay, which brings us to our next unit, which is mole fraction. Mole fraction is the moles of a component over the total moles. So if we take the pressure of gas 1 over the pressure total, then that's N1 moles of gas 1 RT over V divided by the total moles RT over V. So what ends up happening is these cancel and we're left with this form right here. Well, if you look at this portion only, that's mole fraction. So the net effect is if you want to rewrite this, this is P1 PT is equal to the mole fraction of 1. That means the pressure of gas 1 is equal to the mole fraction of gas 1 times the total pressure. So that allows us to calculate the pressure based strictly on moles. So for 1A, a mixture of gases contains moles of hydrogen, nitrogen, and argon. What's the mole fraction of argon and nitrogen? Well, the first thing we need to do is calculate the total moles, which is 1.222 moles. So for, and I'm going to go ahead and do all of them. So the mole fraction of hydrogen would be equal to 0.282 over 1.222. Now, it's moles over moles, so when you get a mole fraction, you just end up with a number. So you end up with 0.230769. So if we're doing 3 significant figures, that'd be 2.31. Okay, so for nitrogen, it's going to be 0.543 moles over 1.222 moles. And for the mole fraction of argon, it would be 0.3937 moles divided by the total moles, which means we get 0.443535, which is 0.44. Whoops, I missed a 4 in there. 4. This one is 0.3248773, which is 0.325. So what this allowed us to do is calculate the mole fraction of each component. So for B, we're told that the pressure in the container, so that's the pressure total, is 2.38 atmospheres. What is the pressure of hydrogen and argon? So the pressure of hydrogen is going to be equal to the mole fraction of hydrogen times the pressure total, which means our mole fraction of hydrogen was 0.231, and it's 238 atmospheres. So it's 0.550 atmospheres. For argon, it's the mole fraction of argon times pressure total, which is 0.44. No, that's neon. Argon was 0.325, 2.38 atmospheres, which is equal to 0.774. If we were to go ahead and do nitrogen, Our pressure is 1.06 atmospheres of nitrogen. So if we were to add those three together, we should get back to 2.38 because, again, they're partials and they are additive. Okay, so what would the total pressure be in a 6.24 liter at that temperature containing how many grams of argon and neon? So the first one we have is volume is 6.24 liters. Temperature is 19.8 degrees C, which is 292.95 K. And we're looking for pressure, but we want the total pressure, which means what we're missing is the moles. So we're going to need moles of argon plus moles of krypton. Well, how do we find them? Well, if we have moles of argon, we'll come over here and say 2.11 grams of argon. The molecular weight of argon is 39.948 grams per 1 mole. That gives us a whopping 0.052819 moles of krypton. It's 3.08 grams. The atomic weight of krypton, another noble gas, is 83.80 grams per 1 mole. That gives us 0.03675 moles, 74 moles. So if we combine these, in total is going to be 0.089573. So we would put that in as 0.089573. So PV is equal to nRT. So pressure is equal to nRT over V. N is the total moles, which is 0.089573 moles. R is 0.08206 liter atmospheres per mole K. I will give you this value, but if you haven't figured it out, you pretty much got it memorized already. 292.95 K divided by my volume, which is 6.24 liters. So I do my math, and again, I'm canceling my units. That's a liter. Okay, so I am left with 0.34508 atmospheres. So if we're using three significant figures, it'd be 0.345 atmospheres. If we were using 4, it'd be 0.3451 atmospheres, and that is the pressure total in that container. And the only thing different about this from the other ones is we had to combine the 2 moles. What would be the total pressure in a 2.4 liter container if it contains 6 million argon with argon equal to 271? All right, wait a minute. So I've got my volume, I've got my temperature, I've got the moles of argon, and there's my total mole fraction. So wait a minute. Pressure total is going to be equal to the mole fraction of argon times, no, that's the pressure of argon is equal to the pressure total. So we know the pressure of argon. It's 654 millimeters of mercury. We know our mole fraction, which is 0.271. So that means that we can find PT. Now, I didn't specify that this had to be in atmospheres or anything else. So pressure total is going to be equal to 2413.2841 millimeters of mercury. Now, if for some reason I asked for it in atmospheres, you could do 760 millimeters of mercury per 1 atmosphere is equal to 2413.2841 divided by, oh, I forgot the 2. So I'm inserting the 2. I got 3.17537 atmospheres. So if I was looking for an answer in, let's say, 4 significant figures, And you could wanted to give it to me in millimeters of mercury or torr, it'd be 2413 millimeters of mercury. Over here it is 3.175 atmospheres if you're looking for 4. If I don't specify, give it to me in whatever unit you want. And again, if I was hand grading it, it wouldn't matter. But let me tell you, if you haven't figured out D2L's cruising, it is very ticky. And so I will specify the unit on the grounds that it will drive you and me insane. Okay. Now, why is this useful? We're doing collection over water. When we get to gas stoichiometry and the gas lab, both of the gas labs that we're doing at the beginning of the week, you're going to need to do, you're going to have to worry about the water, because your pressure total is equal to whatever your product is plus water. Because if you're collecting over water, and we did this in the first gas law lab where we were doing a temperature volume, and we did it in the second one when we were doing something that looked much more similar to this, except we weren't using zinc, we were using magnesium. So in these particular cases, we have to worry about the water vapor that's in the air. So this is what it looks like, but when we do the math, this is more what we have. We'll need the vapor pressure of water, which we look up in a chart. So you're not expected to know that. You can calculate it, but more often you're going to be given it. Okay, the only trick you need to do is make sure the units are the same. So if the sample is collected over water at 21 degrees and has a pressure of 725, what is the dry sample? Well, the pressure total is going to be equal to the pressure of water plus the pressure of the dry sample. So if we're at 21, we have a pressure total of 725.0, and our water vapor at 21 is 18.65, and these are both in torr. Then the pressure of the dry is strictly subtracted. So pressure of the dry is going to be equal to 706.35 torr. Okay, and if we were doing scientific notation for this one, we have 2 digits after the decimal and we have 1 there, so it'd be 706.4 torr using our significant figures. Okay, if it's collected over 44 degrees and has a pressure of 101.24 atmospheres. Now, in this particular case, we have to go one way or the other. Now, I like to go to torr. So my pressure total is going to be 1.240 atmospheres. And I know that 1 atmosphere is equal to 760 torr. So I know my pressure total is 942.4 torr. And we're going to subtract, so this is the pressure total. We're going to subtract the water vapor at 44, that's 68.26 torr. And you'll end up with 874.14 torr. We've got one place after the decimal, so it'd be 874.1 torr using significant figures. So that would give you the value. Now, you could have converted the torr up here to atmospheres and then subtracted it. It doesn't matter. That may have been smarter based upon C. What is the volume of the sample in part B? If 0.026 moles were produced, okay, fine. So my pressure is 874.1 torr, and we know that there are 760 torr in 1 atmosphere. So we end up with 1.15013 atmospheres. Our temperature, we said, was 44.8 degrees C, which means it's 317.15 K. We're looking for our volume. We're given moles. This is N. So PV equals nRT. So volume is equal to nRT divided by P, which is 0.026 moles, times 0.08206 liter atmospheres per mole K, times temperature, which is 317.15 K, divided by my pressure, which is 1.15013 atmospheres. So when we do the math, we end up with 0.5883322 liters. So if I tell you to report it in three significant figures, it'd be 0.588 liters. Now, if I ask for three significant figures in milliliters, it'd be 588 milliliters. So, again, that needs to be specified, especially in D2L. So, this isn't the only time that this is going to be used. We will actually use it in lab. This problem is more like anything in lab than any other problem we've got here. And this brings in stoichiometry. And when you do stoichiometry in gas laws, you have two options. You either do the stoichiometry first to get the moles to go into the gas law, or you do the gas law first to produce the moles to go into the stoichiometry. So you just need to ask yourself, are we doing stoichiometry first or gas laws first? So we're collecting over water, and reaction is producing oxygen. So how many moles of oxygen were collected? So that means that this is a gas law problem. So our vapor pressure is at 25 degrees, is given there. So this is the pressure of water. All right, this is temperature in degrees C. So it's 298.15 K. So our volume here is equal to 0.035 liters. And we have a total pressure of 745 torr. So my pressure of oxygen dry is equal to my pressure total minus my pressure of the water vapor. So that means it's going to be 745 torr minus 27.28 torr, which means my pressure of oxygen comes out equal to 717.72 torr. But I can't have that in torr. I need 760 torr. It's 1 atmosphere. So my pressure comes out to be 0.9443685. 4 atmospheres. Okay, so there's my pressure. So PV equals nRT, but we're looking for N. So N is equal to PV over RT, which means it's our pressure, 0.94436 atmospheres. Again, if you carry it out more than 4 digits, you're fine. Volume is 0.035 liters. R is 0.08206 liter atmospheres per mole K. And temperature is 298.15 K. So again, my K's canceled, my liters canceled, my atmospheres, and I've got 1 divided by 1 over moles, which kicks it forward. So we end up with 0.0013596 moles. We're going to report in 4 significant figures. So we produce 0.001351 moles of oxygen. Okay, so then that brings us to B. How many grams of potassium chlorate decompose? So we're looking for grams of potassium chlorate. So that means we're going to start with what we're given, which is our moles. Now remember the rules. We have to have the moles to go through the equation, but we don't have to go backwards. So we have moles of oxygen when we look at our equation. We have 3 moles of oxygen for every 1 mole. No, for every 2 mole of potassium chlorate. And we know that 1 mole of potassium chlorate, when we look it up on the periodic table, is 122.5492 grams of, forgot the O, potassium chlorate. So my moles cancel and I'm left with grams, so I end up with 0.011. Nope, I don't. I added a 0 in there. I end up with 0.1103759.8. We started with 4 significant figures. Everything has at least 4, so we'll end up with 0.1104 grams of potassium chlorate. Chlorate, not perchlorate. Okay, what percentage by mass of the sample was KClO3? So that means I need my grams of KClO3 divided by my grams of sample times 100. So that means that I ended up with 0.1104 grams of the potassium chlorate. Wait, how much was my total sample? Oh, a 0.250250 gram sample times 100 is equal to a whopping 44.16%. And since all of them had, the second one only had 3 significant figures, we'll do 44.2% is my sample mass. So the beauty of this, or ugliness, is we're back to stoichiometry. I told you it would come together again and we would use it again. So we're going to do a couple more problems. First one is a drain cleaner. And remember the rule of thumb, if you're involving gases, you will either do the gas law first or the stoichiometry first, whichever one you need. A drain cleaner is poured in the heat generated and the gas. So the gas we've got is hydrogen gas. So we're good with grams of aluminum, excess sodium hydroxide. What volume of gaseous hydrogen are measured is produced. So if we look at what we have, we can convert this to atmospheres by dividing by 760. So that's 0.988158 atmospheres. Our temperature goes to 294.95. Okay, we're looking for volume. But the other thing that's missing is moles. So we're going to get the moles from the stoichiometry. So we need the moles of hydrogen. Now be careful, when we did stoichiometry before, we always went to milliliters using molarity, or we went to grams using molecular weight. Here we don't have to do that. So we'll start with 7.21 grams of aluminum. We look at the atomic mass, which is 26.9815 grams of aluminum, or as the British say, aluminium. 1 mole of aluminium. And we know that 2 moles of aluminum goes with 3 moles of hydrogen. Now, we want the moles of hydrogen, so we're going to stop there. So we get 4.008296 moles. We've got 3 significant figures, so we're going to stick with 0.401 moles of hydrogen gas that's generated. Now, we got PV equals nRT. We now are looking for volume, so volume is equal to nRT over pressure. We know the moles, which is 0.401 moles. We know our gas constant, 0.08206 liter atmospheres per mole K. Our temperature, we already calculated, 294.95. Our pressure is 0.988158 atmospheres. So then we generate 9.821953976 liters, which again, we're using 3 significant figures, so that's 9.82 liters. So that much aluminum, which is really not a huge amount, in this drain cleaner will produce 9.8 liters, which is over 2 gallons if you're used to gallons. So that's how we can generate these values is, again, you do either gas laws first or stoichiometry second or vice versa. So on that one we did stoichiometry, then we did gas laws. Now this is one that I like because this is actually useful. Automobile airbags generate, when they're deployed, nitrogen from sodium azide decomposition, because sodium azide is shock sensitive. So it's 65.00987 grams per mole. Went ahead and just did that. How many grams of sodium azide are needed to generate 60 liters of nitrogen in 1 atmosphere? So there's our volume, there's our pressure, here's our temperature, and it'd be 299.15 K. So the question is we need the grams of sodium azide, but we need them from the nitrogen. We get the nitrogen moles from the gas law. So we're going to do our gas law first here. So PV equals nRT. N is what we're looking for. That's PV over RT. So our pressure is 1 atmosphere. Our volume is 60 liters. Wow, that's a lot. Our R is 0.08206 liter atmospheres per mole K. Yeah, it takes a second to write that, but let me tell you, by writing that, you make sure that your units are correct. So this cancels. My liters cancel. My atmospheres cancel. I've got 1 over 1 mole, which means I've got a whopping 2.444166 moles of hydrogen gas. We're going to use, let's see how many significant figures. We'll use 3 significant figures here. So that's 2.44 moles. Whoops, not hydrogen, nitrogen. So now we want grams of sodium azide. So we're going to start with moles of nitrogen. And we know that there are 3 moles of nitrogen for every 2 moles of sodium azide. And 1 mole of sodium azide is equal to 65.00987 grams. So when we do the math, we end up with 105.92995. I used a slightly different moles, but we're going to use 3 significant figures. So we would end up with 106 grams of sodium azide. Forgot to look at what I was doing. So you will definitely have a problem like this on the test where you go from the gas law to stoichiometry or from stoichiometry to the gas laws. The hard part is figuring out which one is going to go first. And if you read the problem, it's usually easy to identify because one of them is going to give you the moles easily and one of them is not. So I think we only have one more section left of this chapter after this. So here we go.